So first we have the sum law, which says if you take two functions, maybe call them f of x, g of x, and I'll draw some graphs that these might look like, okay? So maybe f of x looks like, let's make f of x a line with a hole in it. So let's say 1, 2, 3, maybe there's a hole right there. And so now you know that, for instance, the limit of f of x as x goes to a, well, let's take a equals 1, 2, 3. So just bring your finger on over to the point 3 and what's happening to the y values. So I'm going to track x and f of x. Here we go. And you can see as x goes to 3, f of x, the y value is heading towards 3 as well. In fact, I've just drawn the graph of y equals x with a little hole there. And g could be anything. So let's say that, actually, let's just make g a constant function. In the graph, g is equal to 4. It's just a horizontal line. But the limit laws work for any functions, not just f and g. And the sum law says that if you take the limit as x approaches a particular value, in the picture it's 3, if you take the limit of the sum f of x plus g of x, then the answer that you're going to get is the limit of f of x plus, running into my graph there, plus the limit of g of x. So in other words, if you take the sum of those two functions, then the limit of the sum is equal to the sum of the limits. And so here I can even draw what the sum is for you. So since this is just the constant function, g equals 4, the sum is just going to translate this straight line up 4 units. So if I walk upwards 1, 2, 3, 4, there I go. There's f of x plus g of x. And so you can kind of see this is true from the picture, because if I take the limit as x goes to 3 of the blue function f, I get 3. If I take the limit as x goes to 3 of the yellow function g, that's still going to be 4. G is the constant function 4. You add those together, you're going to get 7. And it's not completely easy to see from the picture because I didn't continue to include the scale. But what I've done with the sum is just translating it up 4 units. So you can see that as x goes to 3, the orange function is going to stay up at 7. So it really is the sum of the two limits. And that's going to work whenever you know that the functions actually have limits. Okay, so I'm getting some feedback that maybe that's difficult to see through the screen share. So I'll leave that for now as something that you can watch to reinforce. But all these topics that we're going to cover, I have a video series on them to introduce you to them and refresh them. So I really recommend making that part of your study here. But for today, I'll briefly go through and we also introduce them on the big boards in the video here. So what are these limit laws saying? Limit laws are telling us how to create or how to determine new limits based on old ones. So just to help us review, so what if I had limit as x goes to 3 of x. So this is like the simplest, one of the simplest questions you could ask. Like you draw the graph of y equals x. So algebraically, certainly you know that if x is tending towards 3, then x tends towards 3. So there's no problem with that. Here's x equals 3, y equals 3. X and y have the same value. But what if you take something like limit of x, limit as x goes to 3 of x squared? Well, your first thought or your first guess might be, well, maybe I can just substitute in like x equals 3 and get 9. And you're right, that's totally true. And you can see it from the graph. If you look at x goes to 3, you know, depending on how well the graph is drawn, you'll have x equals 3, y equals 9, and then you can see as your x values are getting close to 3, your y values are getting quite close to 9. But still, you might feel a little bit uncomfortable. Like you might say, like, how do I definitely know this is true without just saying something like, well, the graph looks like it's true. And the limit laws can come into play and help you do this. Because we have one limit law that says that if you take the limit as x goes to a point, a, if you take the limit of a product of two functions, say f of x and g of x, then the answer is going to be the product of the limits. So it's going to be the limit as x goes to a of f of x times that limit as x goes to a. Of g of x. So this is called a limit law. The limit of the product of the functions is a product of the limits. So like if you can agree with me as a baseline that like something like this is definitely true, limit of x as x goes to 3 is equal to 3. Then if someone says like calculate the limit of x squared as x goes to 3 using the limit laws, you can say, okay, well that's definitely going to be taking f of x equals x, taking g of x equals x, that's definitely going to be limit of x as x goes to 3 times the limit as x goes to 3 of x, which is going to be 3 times 3. X goes to 3, excuse me. It's going to be 3 times 3, which is 9. So these limit laws, all of them are just tools that allow us to take simpler limits, things that we know, and then combine them to find other kinds of limits. So I'll check for questions. Okay. Another example. If you remember last time, we looked at f of x equals sine x over x. As x goes to 0 of f of x was equal to 1. So we found that out by drawing the graph of sine x over x on the graphing software and just observing it, seeing that answer was equal to 1. So even though sine x over x is not defined when x equals 0, it's something we call an indeterminate form. It's also true that the limit is still equal to 1, that is to say, sine x over x, the y values there, they approach the number 1 as x. Approaches 0. But now say that you wanted to find something else. So there's a question like, why does multiplication apply here? So I'm thinking x times x is x squared. So it's the limit of f of x equals x times the limit of g of x equals x, which is equal to the limit of f times g, which is x squared. Let me give you another example to work on now. So let's take a problem like this. So what if I wanted to find the limit as x goes to 0 of, let's say, x squared plus 1 times sine x over x. So this entire thing. So let's say I asked you that problem on homework or a test, and I'll give you 30 seconds to think about it. So how do you use a limit law to calculate this limit using what you already know? So take a moment and think about that. So after giving you some time to think, would anybody like to volunteer, either out loud or in chat, a strategy you might use to use that multiplication limit law in order to calculate like what that limit is equal to? Okay, well, I'll go ahead and give it a shot. So I'll just say, since I know that limit of sine x over x is equal to 1, since I know that already, That's what I want to use to solve this problem. So in fact, I want to break this up as, maybe I'll take this to be my g of x. Maybe I'll take this to be my f of x. So that I've got the limit now of f of x times g of x. And the limit law says that this is going to be the limit as x goes to 0 of f of x times the limit as x goes to 0 of g of x. So I've reduced the problem to calculating each of these limits individually. Now, what about this limit as x goes to 0 of x squared plus 1? So since it's possible to simply substitute in x equals 0 and get an answer, like whenever it's possible to do that, that's your clue that that's probably going to be the right answer. And in fact, it's true, the limit as x goes to 0 of x squared plus 1 is equal to 1. You can substitute in x equals 0 and you'll get 0 plus 1. Like, how would you definitely, without a shadow of a doubt, prove this to yourself? Well, you could use this limit law that we saw in the first video, the sum limit law. But I know maybe that was a little blurry, so I'll state it here. It says that if you have a limit as x goes to a point of a sum of two functions, then that is going to be equal to the limit of the first term plus the limit of the second term. As long as the limits exist, it'll always be true that the limit of the sum is equal to the limit of the first one plus the limit of the second one. So we say the limit of the sum is equal to the sum of the limits. And so how you might use that here is you might just say limit as x goes to 0 of x squared plus 1 is going to be limit as x goes to 0 of x squared plus limit x goes to 0 of the number 1. You could even break down x squared even further and say this is limit of x times x. At this point, we're pretty happy just saying, well, you know, limit as x goes to 0 of x squared is equal to 0. That's not a big problem. And the number 1 is constant. It doesn't depend on x. X can do whatever it wants. 1 stays constant. So this is equal to 0 plus 1 equals 1. So that's the limit laws, the sum law working for you, telling you something that you already knew, that limit as x goes to 0 of x squared plus 1 is equal to 1. Okay, so zooming out back now to this larger problem. This first limit of f of x, was limit of x squared plus 1, was equal to 1. So I calculated that, so that's 1. The limit of the second one, limit as x goes to 0 of sine x over x, we calculated that using a graph last time, found it's also equal to 1. So the limit of the product is the product of the limits equals 1 times 1 equals 1. So are there any questions on how I calculated that? And I'll even share with you the graph. So that was an investigation of the limit using the limit laws. You could also have just straight up investigated it graphically. And I've drawn for you the graph of x squared plus 1 times sine x over x. And here's what it looks like. And you can see that as x goes to 0, those y values are closing in on 1. Even though the function is undefined at x equals 0, because you can't divide by 0, it's still true that the y values are approaching the number 1 as the x values approach 0. Check out page 76 for the other ones. I mean, there's a constant multiple law. If you multiply a function by a constant, then the limit of that is going to be constant times the limit. And there's a limit law for quotients, which I'll go ahead and write down, but you don't really need me to just be like writing down all the stuff that's already in the book. I think you really need me to be working through exercises, so won't spend too much time on it, but like as an example, limit as x goes to a of f of x over g of x. Like if it's true that this limit exists, and if you know that the limit as x goes to a of g of x exists and is not equal to 0, then you can say this is like limit of f of x. So x goes to a over limit of g of x as x goes to a. So definitely this is not going to be true if the denominator limits to 0. For instance, like if you take the limit as x goes to 0 of sine x over x, you definitely can't say that because of the limit laws, this is going to be equal to limit of sine x, x goes to 0 over limit of x. Because if you try to do this, you're just going to get 0 over 0, which is what we call an indeterminate form. That's not helpful for you. So this limit law does not say that. So we have to X that out. This limit law has the condition that as long as your denominator, the limit exists and is not equal to 0, then you can split it up like that. So this limit law is useful for calculating limits of things like if I had 2x plus 3 over 3x squared plus 1, and I wanted to calculate the limit as x goes to 2. Then you could use the quotient limit law. You could write as limit as the top part over limit of the bottom part. Then you could use the sum law to break it up further and finally get the result. In fact, take 30 seconds and go ahead and work this problem using that quotient limit law. And then tell me what answer you get. And then I'll pause too to answer any questions. Okay, after giving you a moment to think, I'll write out my answer too. And I'll stress it's not just finding the answer, it's also demonstrating our thought process. And the thought process is that we know some basic limits, like limit of a constant, like limit as x goes to a of the number 3 is equal to 3 no matter what. Limit as x goes to a of x is equal to a no matter what. And then from that, you can multiply and add things together to then determine limits of any polynomial or any rational function, so long as that denominator is not tending towards 0. So for a setup like this, the instructions are often going to be, say, use the limit laws to determine the value of the limit. So even though, like, you and I will both know, okay, I can just plug in the number 2 and it's going to give me the result. The point here is to make use of those limit laws to demonstrate that the limit is what it is. And so what you can do is you can say, well, I can rewrite this as limit of 2x plus 3 over limit of 3x squared plus 1. I can do that because the limit of 3x squared plus 1 is not going to turn out to be 0. And what's going to happen is limit as x goes to 2 of 2x plus 3 is going to be 4 plus 3 is 7. And this one is going to be 3 times 4 is 12 plus 1, which is going to be 13. But in order to get there, you use a couple more limit laws. You want to use the sum law to break up the sum. So you might write this as limit x goes to 2x plus limit x goes to 2 of 3, everything divided by limit x goes to 2, 3x squared plus limit x goes to 2 of 1, and then you're almost there. One of the limit laws you'll see on page 76 is this constant multiple law, which says, look, if you take the limit as x goes to 2 of 2 times x, that's the same thing as 2 times the limit as x goes to 2 of x. So not to put too fine a point on it, but like you can do one more step. Basically pulling out that 2, that's the constant multiple limit law. And here you can combine the constant multiple limit law. So this would be the constant multiple law, pulling out that constant. And as before, x squared is equal to x times x. So the limit as x goes to 2 of x squared would be by the product limit law, that would be the square of the limits. And then finally, you get limit as x goes to 2 of the number 1. So the point of the limit laws is you can break things down like this to a place where they're so simple that all these individual limits are really completely clear to you. Like the limit as x goes to 2 of x is definitely going to be 2. Limit of the number 3 as x goes to 2 is definitely going to be 3. Limit of the number 1 as x goes to 2 is definitely going to be 1. So finally, you get 2 times 2 plus 3 over 3 times 4. So 3 times 2 squared plus 1, which finally turns out to be 4 plus 3 is 7 over 13. So there's usually two different reactions to this. One reaction is what the heck is going on? That's like an office hour question. The other reaction is, why do I need to write all that out? That doesn't seem necessary at all. It's obvious to me that I could just plug in x equals 2 and get 7/13. And what I would say to that is, yeah, that's true, but the point of the exercise is not to learn that the limit was 7/13. The point of the exercise was to demonstrate that you can break down the problem into pieces that are so small that they only involve like limit as x goes to 2 of x, limit as or limit as x goes to 2 of a constant. And these particular limits we're so comfortable with. Those are sort of like the atomic pieces. So when you're given a problem like calculate this limit using the limit laws, you're really going back to breaking something down to its atomic level, where you're only using these simple limits that you're like definitely know are true without any work. Or you're using something like sine x over x that we've kind of already calculated in class. But as we move forwards, yeah, you're not going to be doing this every time. You're not going to be required to just do a bunch of busy work. This is definitely to get you familiar with using the limit laws in more nuanced situations that will come later. Just a couple more things, a couple more concepts to introduce. Before I go on and erase the board, any questions or comments or anything I can discuss? Okay, so the other thing that I want to talk about regarding limits is this idea of a left-hand limit versus a right-hand limit. So for instance, let's look at the following function. So let's say this is x equals 3. Let's say that this is 4. And this is 7. So this is what we call a step function. This is a graph of function f of x, and f of x has a formula. It's given by f of x is equal to 4 if x is less than or equal to 3, and f of x is equal to 7 if x is strictly bigger than 3. And so like my first question, I could ask you a series of questions. So the first question is, does the limit as x approaches 3 of f of x, does this limit exist? Which is to say, is there a single number L such that f of x is definitely close to L if x is close to 3? What do you think? A couple more moments if you'd like to respond. Okay, so I'll do a discussion of this. What I'm thinking is I have to go back and try to remember what's the definition of limit. And the definition of limit is to say that the limit of some function is equal to a number L if it's true that whenever your x value is close to 3, your y values are close to that number. So I'll draw, well, I don't have my other colors here today, but I'll highlight, here's the range of values in the domain that are very close to 3. And here's the corresponding values in the range. And some of those values are 4, and others of those values are 7. So even as the x values stay very close to 3 on one side or the other, the y values could perhaps jump from 4 to 7. So in fact, this limit, we say the limit does not exist because it's not true that there is a single number where those y values, those values of the function, are close to that single number if x is close to 3. On the other hand, it is true that if I only approach 3 from the left, if I only consider those values of x that are less than 3, then my y values are going to hold constant. They're going to be equal to 4. So what I do is I call that a left-hand limit. And I denote that by writing limit as x approaches 3 from the left. You put a little minus sign in the superscript. So we do say that the left-hand limit of f of x is equal to 4. Meaning that if I consider values of x that are close to 3, but also only less than 3, then the corresponding y values are going to be very close to 4, in this case, literally equal to 4.
I have a question about this.
On the other hand, I could do what's called a right-hand limit. And I could only consider those values that are both close to 3, but also bigger than 3. And in that case, I'm really just looking at this part of the graph, and I'm saying, okay, when x is close to 3, but bigger than 3, then my y values are all very close to 7. And in this case, they're actually equal to 7. It doesn't matter that the actual value, f of 3 equals 4. That doesn't affect the limit. The limit is only asking the question. As x approaches 3, what do the y values approach? And they approach the number 7. So right-hand limit, you would denote that by saying as x approaches 3 from the right, so a plus in the superscript of f of x, then that's equal to 7. And let me pause for questions or comments that you may have typed in, or you could say them out loud if you like.
I have a question.
Yeah.
So you keep using the word approaches or close to or around in reference to like the limits.
Yeah.
Does that mean that I could, like, this limit is defined as a range, or is it always going to be one number?
The limit will always be one number. The terminology that I'm using is a little bit loose because I'm not using the exact precise definition. But think about it like this. So here's why we have to talk like this. Like if you go back to sine x over x, and you want to say something like limit as x goes to 0 of sine x over x equals 1. So if you want to make a statement like that, then you know that you can't simply plug in the value x equals 0, but you want to find a way mathematically to formalize the idea that clearly you could just fill in the graph with the number 1 and it makes this nice continuous shape. And so the concept of a limit is what does that. And so the way you can think about it is you can say, okay, well, let's let you pick any number that you want. So you could pick like 1 over 10,000. And you can say, okay, like if I look at all the y values that are within 1/10,000th of the number 1, so like here's the number 1, and I'll draw 1/10,000th like big, so just you can see it. So like 1 point, maybe it should be that. And here's 1 minus 1/10,000th, which is like 0.999. So you can pick a range. So there's where you're allowed to pick a range. But then what I say is once you've picked that range, there must exist an interval around 0 so small that if you're in that interval, then all the y values are going to be in the range that you picked. And if you now pick 1 over 100,000 and shrink this, I'll be able to correspondingly shrink my range in the domain. And we can just play this game over and over again so that no matter how small of a band around the number 1 you pick, I can find a very small band of x values in which, that make the y values like within that range. So there is that game that you can play. And if it's possible to play that game for any number you pick, no matter how small, then we say that the limit of sine x over x is equal to 1. But you'll hear me describing that informally just by saying that as x values get close to 0, the y values get close to 1. But that's the process that I'm referring to, that if you challenge me with any small range of y values above and below 1, I can respond to that challenge by finding a small range of x values very close to 0, so that if x is in that range, then the y value is within the range that you picked.
Yeah,
Does that make sense?
Yeah. Thanks.
And if you take a real analysis class, math 312 and 313, then you'll explore all those formal definitions and like how to argue in that way in a great depth. Okay, so that was section 2.4. Learning objectives for today were limit laws, left-hand limits, right-hand limits, and we'll see also the series that I put on there with like more examples. Next time is section 2.4, that's continuity. So you can study that in advance for Wednesday, and you can also look at my videos on YouTube on continuity to watch before the lesson. So once again, office hours at 3:30, homework due at 5, and we'll see you next time for sure on Wednesday. Have a great day.
Thank you. Bye.
Take care.